Good morning, everyone. Welcome to the first briefing here on Thursday morning at the 229th AAS meeting at the Gaylord Texan in Grapevine, Texas. I'm Rick Fienberg, AAS press officer, and I'm assisted today by my two deputy press officers, Inga Heyer in the back, who's monitoring our webcast, and Larry Marshall, who will be handling the microphone during the Q&A. If you have a phone on you or a pager or a beep or anything like that, please silence it. 3 press releases are going out on the AAS press list this morning. They'll be in your inbox when you get back from the briefing. And I wanted to make a couple of quick announcements. First, today during the lunch hour is the NASA Town Hall, and Felicia Chu, one of the public information officers at headquarters, has arranged for Paul Hertz and Thomas Zurbuchen to be available to the media this afternoon, so that if you can't make the town hall or they run out of time for Q&A and you still have some questions, you can meet with them. So Paul is the director of the NASA Astrophysics Division. He'll be available from 3 to 3:30. And Thomas Zurbuchen, the new associate administrator for the Science Mission Directorate, the successor to John Grunsfeld, who many of you know, will be available from 5 to 6 today. And that'll be in Pecos 2, the press interview room over on the hotel side. Finally, I got 2 more. If you were interested or are interested in interviewing either of our 2 underage astronomers, Carson or Cannon Huey Yu, who are giving a poster tomorrow, I'm going to put a sign-up sheet on the bulletin board because they're a little concerned about being mobbed. So you'll sign up to meet with them. And finally, if you haven't signed up for the press dinner yet and you'd like to join us tomorrow evening in town, we're going to actually escape the hermetically sealed Gaylord Texan. Please sign up in the press office. All right. So I don't know if I've ever been to a AAS meeting, and I've been going for 30-odd years, without at least one press conference on black holes. And today we're going to be talking about galaxies and the black holes they're in. And you know that those are there are different kinds of black holes, and I think we're going to be hearing about different kinds of black holes. We have 3 presentations, and as I said, there will be a press release going with each one. We're going to begin this morning with Neil Brandt from Penn State. He'll talk about the growth of black holes revealed by the deepest ever X-ray image. And I should note that Dr. Brandt will be giving his Bruno Rossi Prize lecture this afternoon. Bruno Rossi Prize is given by our High Energy Astrophysics Division. He'll be followed by Reinout van Weeren from the Harvard-Smithsonian Center for Astrophysics, who will be speaking about a cosmic double whammy, a black hole blast, followed by a galaxy cluster collision. And finally, Ian Steer from the NASA IPAC Extragalactic database will talk about the explosive growth in the number of redshift-independent galaxy distances, which, as you know, most galaxy distances we think of we're getting from spectral redshifts, but it turns out that those need to be calibrated against something. Otherwise, we can't trust them. So we're going to learn about a huge new database of independent distance estimates, which of course will help dramatically with the study of the supermassive black holes within those galaxies. With that, I'll turn it over to Neil Brandt, and we'll get started.
Okay, well, thank you all for coming. So today I'd like to tell you about some work that the Chandra Deep Fields team has been doing to investigate the growth of black holes revealed by the deepest ever X-ray image. And this image that I show there on the left is in fact the central part of the so-called Chandra Deep Field South. And over the past couple of years, we've now pushed that up to an 81-day exposure with the Chandra X-ray Observatory. So this is an extremely sensitive observation. You're seeing the central part of the field here. And this field is in the southern sky. It's in the constellation of Fornax. And most of the X-ray sources that we detect in this field, and the sources there are color-coded by their precise X-ray spectral properties, are accreting supermassive black holes in the centers of galaxies. And so that little speck that I have, that little green-colored speck with the arrow pointing next to it, that little speck represents what I show there on the right, a supermassive black hole that's actively accreting material, and it has not only an accretion disk around it, but has a high temperature coronal structure up above the disk, and Compton scattering and other processes produce the X-ray emission that we're seeing. And so that's what makes the X-ray emission that we're detecting from most of these active galaxies. And most of those little dots you see in that image represent one of those things. Have a number of points to make about this image. So currently in our entire field, and again you're just seeing the central part of it there, we detect about 1,055 X-ray sources. This is the best, the most representative AGN sample that we believe we have so far, reaching out into the very distant universe. So we're trying to get a complete census of all the supermassive black hole growth that is out there. And X-rays are really powerful in that regime for one reason, because they're very penetrating. The same reason why your doctor or your dentist use X-rays to look at your bones or your teeth is why we use X-rays here. The X-rays can penetrate out of obscured material that we commonly know is present in the centers of galaxies. The density of supermassive black holes that we detect in this observation is the deepest that's ever been seen on the sky. If you scale up the sky density that we have here to the entire sky, and we think that's valid, we think this is a representative patch of sky, there'd be about 1 billion of these active galaxies over the entire sky. So that's our census of these supermassive black holes. Another point I want to make just sort of goes to the incredible design of Chandra. The faintest forces that we detect in this field, we're detecting one photon coming in from them every 10 days. And if you can build an observatory that can detect one photon coming in every 10 days, you should be pretty happy that you've done a good job. Okay. And furthermore, Chandra doesn't only make an image here, it also gathers spectral information for all the sources. Another reason why we wanted to go have such a long exposure is to gather X-ray spectral information for all these sources, better than we had before. We can also study the long-term variability of these sources, and we have great multi-wavelength data in this field. And then the final point I want to make here is that these observations are all publicly available. You can all go home tonight and download them onto your Macs or your PCs if you like. And furthermore, just a couple of days ago, we've published the catalog, making all the source properties that we're able to measure available. Just to sort of show you a few points about the multi-wavelength data, here are Hubble Space Telescope images of just a few of the X-ray sources that we detect in the field. We have page after page of these things, and you can see that some of the X-ray sources are associated with very optically bright galaxies, some with very faint galaxies, and these images here are colored. These are actually composites of 3 different Hubble images, made with blue light, and with red light, and then with infrared light, and that gives us color information, lets us characterize the types of galaxies in which these supermassive black holes are growing. We've worked very hard on getting all these counterparts. Having all that multi-wavelength data is essential to get counterparts. And so far, with an enormous amount of work, both in our group as well as by the whole community, we now have identifications and good redshifts for about 98% of the X-ray sources. So this has been almost 2 decades now of effort getting there. And it's very gratifying to finally be there, to have this really good census where we've characterized where these things are out in the universe in a highly reliable manner. And that's taken an enormous amount of work by many people to get there. We find that active galactic nuclei, these accreting supermassive black holes, are the majority of the source class, but we also detect a significant number of non-active galaxies, where there we're detecting binary star systems containing stellar mass black holes that weigh 10 times the mass of our sun, round numbers, or neutron stars that produce a lot of the X-ray emission. And this plot here shows the redshift distribution. Along the top axis, I show the look-back time, okay, from this paper that Ben Luo has recently led, showing that our sample spans most of cosmic history well. You can see from this plot for the active galaxies, which is the red histogram there, that we have good source numbers ranging all the way from about 3.5 billion years ago out to about 12 billion years ago. And our most distant sources, we're reaching back to about 12.5 billion years ago in look-back time. And we're doing this again with a highly complete sample where we can find the obscured systems and the unobscured systems, unlike many other surveys. And this sample is a treasure trove. It will be used in many future studies. I can't possibly even begin to tell you all the stuff we've done already, although I will cover some more details in my other talk today. This is more technical, but I want to tell you about one specific project that we've been pushing hard on, and that is trying to learn something about the seeds of the first supermassive black holes in the universe. So I've shown you we detect all these high redshift accreting supermassive black holes. Where do they come from? We'd like to get some insight into that, some observational insight, so we know there's a lot of good speculation out there, but we want to actually try to make some measurements that constrain these ideas. So the best ideas we have are that you start with a lower mass black hole, a seed, that then ultimately grows by eating material and over time grows and grows and grows in mass to become one of these supermassive black holes. And the precise type of seed is uncertain. One possibility is you have what are called light seeds. These would be early X-ray binaries, similar to the binary systems we observe in our own galaxy, but then that grow and grow and grow in the center of an early proto-galaxy to become one of these supermassive black holes. Alternatively, you could have what's called a direct collapse black hole, where gas directly collapses down to form 1,000 or 10,000 or 100,000 solar mass black hole, and then that can grow more easily because you're starting from a higher mass to become one of these supermassive black holes. So that's one thing we're trying to address. What is the nature of these seeds? Are they light or are they heavy? And this is a very challenging work. This goes beyond even the limits of Chandra's direct detection capabilities, and so we've had to use a bit of a trick to get there. And the trick that we use is called stacking. So I want to tell you a little bit about stacking. Here's a romantic example of stacking prepared by Brett Lemur. He's one of my previous graduate students. This is perhaps my favorite image ever made by one of my graduate students. It was very creative. Brett was about to get engaged to his girlfriend, and he was feeling very romantic, and so we put a bunch of tea candles on his stairs, okay? And he took 2 images of the tea candles, one with a 3/100-second exposure, and one with a 1/1000th second exposure. And the idea of this stacking is that if there is information embedded in those lower quality short exposures, you should be able to add up all those individual observations and recover some information about the candle. And you can see that's what we have down there at the bottom. It's a little washed out because of these bright lights shining on the screen, but in this stacked image, you can see by stacking up all of those very short exposures, you can recover a nice image. You can see the flame very well. You can see the candle's wax. You can see even evidence of the wick in there. So that's what this stacking can do. So I thought that was a very creative way to demonstrate the power of stacking. We've done essentially that exact same technique, but for galaxies in the distant universe. And this is work that's been led by Fabio Vito, who's currently a postdoctoral researcher in my group. And so what Fabio and all of us have done is we've gone and stacked up X-ray emission from galaxies found by the Hubble Space Telescope, found by large ground-based observatories that were lived 1 to 2 billion years after the Big Bang. Okay, and we add up the X-ray emission coincident with the positions of where those galaxies are. In the leftmost panel there, we've stacked up the X-ray emission from 1,393 galaxies from redshifts of 3.5 to 4.5. And we're forming there an effective image of 8.2 billion seconds of Chandra time by adding up all these galaxies, each of which has a 7 million second exposure. Okay, and so that's about a 260-year Chandra image. And even though all those galaxies are individually undetected, when you add them all up, you can pull up a detection. There it is. So the middle panel shows even higher redshifts. There we have a 2.7 billion second Chandra observation. We pull up a detection. And at the higher redshifts, we have only a 44-year exposure there, 1.4 billion seconds. We can't get a detection yet, but we aim to get there in the future, and I'll tell you about that. And so there we can get a very useful upper limit about the signal. And when we go and analyze and interpret physically the origin of this signal, we believe most of the signal here comes from X-ray binaries in massive high redshift galaxies. Okay? So it's from these binary star systems, not from supermassive black holes. And in fact, what that is telling us is that most high redshift supermassive black hole accretion had to have occurred in a short, active galactic nucleus phase, and that there isn't much room in the high redshift universe for a continuous low rate of accretion by which these black holes could grow. Furthermore, when we analyze the technical details of how many sources we find at a given luminosity, we find a tentative hint for massive seeds that may be driving this growth. Although I think to firm that up will require much further observational work, as a lot of further theoretical work as well. So that's one of the nice results that we have so far. And in the future, we hope to push this work even further. One great thing now that we have this Chandra data available is when new multi-wavelength data sets are added to the collection, we can analyze our data even better. In particular, we're very excited about the James Webb Space Telescope in this regard, which would find large numbers of galaxies out to redshifts of 10 to 15. And we will then be able to go with these samples of galaxies and stack them up, and we'll have many more galaxies to be stacking, so we'll have 8 billion or 10 billion second observations for those, and we hope to pull up detections and learn something at even higher redshifts about the first supermassive black holes that ever formed in the first massive black holes that ever formed in the universe. And then even in the more distant future, we're very excited about new X-ray missions. People currently are studying a very exciting possible mission called Lynx, that would actually be able to go far beyond Chandra's sensitivity by more than an order of magnitude, more than a factor of 10, perhaps almost a factor of 100 more sensitive than Chandra, that would give us a real prospects of detecting these seeds directly, individually. So that would be a great possibility for the future. And I'll just end by highlighting some of the leaders of this work, in particular the cataloging and all that work. In addition to me, was led by Bin Luo, Yongquan Zhui, and Brett Lemer. And then the stacking work was led by Fabio Vito, Roberto Gilli, and Christian Vignali. And I give the references for the papers there if you're interested in more detail. And I want to mention that we have many other wonderful collaborators on this work and many other ongoing projects. And if you're interested in more details, those are the sessions where I'll be talking at more technical length. Thank you.
Okay, good morning, everyone. Thanks for coming. So I will be talking about an exciting discovery we made, and which was published very recently, that's yesterday, in Nature Astronomy. And to show here, it's on the cover here, this nice image. So I'll be talking about this discovery, which we made using big radio, optical, and the Chandra X-ray satellite. So what you see in this image here is a composite image using Chandra data in blue, radio data here in red, and there's an optical background image from the Subaru telescope. And one of the big mysteries in the field of galaxy cluster science is, where does this radio emission come from, what you see in red, these big giant swirls? And what we knew for about 10 years is that these swirls are related to collisions between galaxy clusters. But we now find out that there's also a link with supermassive black holes in the center of galaxies. And what we find is that particles which are accelerated by the supermassive black hole, they're launched in a jet and then are accelerated a second time when they encounter a shock created by this giant galaxy cluster collision. So what do we know about galaxy clusters? They are the most massive bound objects in the universe, and they typically contain about a few thousand galaxies. And some of these galaxies host supermassive black holes, which are active, so you can see them at radio and X-ray wavelengths, as we saw in the previous presentations. However, most of the mass in galaxy clusters is not in the galaxies, but most of the ordinary mass is in a hot gas, which has a temperature of about 10 to 100 million degrees. So this gas is extremely hot, and it emits at X-ray wavelength. And that's what you can see here in this Hubble image, where you see an image of a galaxy cluster in optical light, and then overlaid on top of that in purple is the X-ray emission from Chandra. So this X-ray emission fills the entire volume, the entire region between the galaxies. Now, how do galaxy clusters form? So galaxy clusters form by collisions of smaller clusters and galaxy groups. Now, during a collision, the galaxies fly mostly past each other without very strongly interacting. However, the gas between the galaxies collides and create giant shock waves. Now, these collisions are the most energetic events in the universe after the Big Bang. However, they last for a very long time. So a typical collision takes about 1 billion years, so that's a very long time. But there's an enormous amount of energy released in this process. And when we look in the radio at this colliding or merging galaxy clusters, so when two smaller clusters collide to form a larger one, what we often see is this radio emission, what you can see here in red. So these are two examples of galaxy clusters here. where again, the X-ray emission is here in blue and the radio emission in red. And you can see this kind of like elongated, funny-looking, very big structures. And the main question we have is, how are these formed? And what we know from observing with radio telescopes is that these particles, what we see in the radio, they have very high energies. They're relativistic electrons, essentially. And once they spiral around magnetic field line in the cluster, they emit at radio wavelengths. And that's what we can observe with radio telescopes. And these kind of radio structures we also call radio relics. And the idea is that these sources trace particles accelerated at shocks created in the gas by cluster collisions. And indeed, if we look with X-ray observations, we can actually detect these shocks, and we can measure the properties of these shocks. So you think, okay, this is fine, the shocks accelerate the particles. But it's not as simple. There's actually a big problem here, because we can measure the strength of these shocks in these clusters, and these shocks are very weak. So they only travel with a speed a few times that of the sound. So here you can see an example here where there's an airplane basically breaking the sound barrier, and these shocks are somewhat similar. And the shocks in clusters so travel only with 1 or 2 times the speed of a sound, which is roughly 2,000 kilometers per second. However, if you want to accelerate particles in a shock, you need a much stronger shock, like a shock which travels more than 10 times the speed of sound, for example. And these shocks do not occur in galaxy clusters, so how can these shocks then accelerate these particles? And to illustrate the problem, so if you want to accelerate a particle, so an electron, from the X-ray emitting gas, so in blue, so there are all electrons emitting, and you want to accelerate it so that it starts emitting radiation at radio wavelengths, you basically need to increase the energy of these electrons by a factor of 1,000,000. So that's a huge energy boost. And these weak shocks can simply not do that. So what is the solution to this problem? So for that, we took observations of this galaxy cluster, which is Able 3411, 3412, where you have this beautiful Chandra image here, where you can see basically a giant collision taking place, where one of the clusters is essentially moving to the hot gas of another cluster, creating this kind of cometary shape. And with the arrow here, you can see the direction of motion of these galaxy clusters. And then on the bottom here, we can see this complicated radio structure here. And I should say here that this image was made with Chandra. The radio image was made with a big radio telescope in India, the GMRT, the Giant Meter Wave Radio Telescope. And the optical background image was made with the Subaru telescope in Hawaii. When we zoom into this image, so in this particular region here, we can actually see what's really going on here, and what is the explanation for this apparent mystery. So what we see is we see a galaxy with a supermassive black hole, as indicated here with the arrow here, and then this supermassive black hole launches a jet of relativistic electrons, and then eventually these electrons encounter shock waves, where they are then again accelerated a second time, producing this complicated swirls of radio emission here. And the shock is indicated here with the yellow dashed line. We can also measure the properties of the shock, and again we find that the shock is very weak. You can see here the Chandra image in orange at the bottom, where you see a very weak kind of jump in the X-ray surface brightness, indicating again this is a very weak shock. So the shock can essentially accelerate particles to these very high energies, because it can accelerate pre-accelerated electrons from the black hole. So first we have the electrons are accelerated in the black hole. They're already very energetic, and then when they encounter the shock, they only require a kind of mild boost in energy to then start emitting in the radio band. And just for a comparison here, I show roughly the size of the Milky Way. So again, to make the point, these are really giant structures. They are much bigger than individual galaxies. So they really span regions about 2 million light years across. So that's kind of like the largest, in some sense, the largest particle accelerators that we know of in the universe. So what is now the real actual evidence that we see what's going on here? And for that, we actually have to look a little bit more into detail into the radio spectrum. So what you can do is you can take measurements at different radio frequencies. So I have shown this plot here where you can see the axis here is the frequency, and on the other axis we have the flux, so that's essentially just the brightness of the radio emission. And if we take measurements at 2 different frequencies, we can measure the slope of the spectrum, as indicated here. So we have steep spectrum radio emission in blue here, and flat spectrum radio emission. And what we know from theory is that flat spectrum radio emission is observed when you have active acceleration, so particles really being accelerated. When you have like the steep spectrum radio emission, that are places where the electrons just lose their energy by radiating and what we can essentially observe. So what we see here, if we map this spectral slope by using this radio observation, we can see where the AGN is, so the supermassive black hole. We see the flat spectrum there. So particles are accelerated in green. Then the particles end up in a jet where they lose the energy, so the color turns into blue. And then when they hit the shock, again, you see the color change to green. So again, indicating a second time acceleration event. So just to recap here, so what we see is we see particles accelerated by a black hole. They receive essentially a second energy boost when they're swept up by these giant shock waves from a galaxy cluster collision. And this kind of explains the mystery why the very weak shocking clusters can still actually produce very bright radio emission. So the black holes essentially really help in this process here. And this is also exciting for future observations because the connections between the AGN, where you have a flat spectrum, and the sites of reacceleration, essentially, where again at the shock, where you again have the green emission, these connections in between are have very steep spectra. So again, that means this emission is only bright at very low frequencies. And the exciting thing is that there are many low-frequency sensitive telescopes are coming online at the moment, such as LOVAR, we have the MWA, and also the upgraded GMRT, and in the somewhat more distant future, the Square Kilometer Array. And all these telescopes are extremely sensitive at low frequencies, so should reveal many of these connections between basically black holes and galaxy cluster shocks. What we still don't know is how these particles are precisely accelerated at a shock, because the theory is extremely complicated here, and even with numerical simulations or with computer models, it's really hard to predict what is exactly going on. And to solve this problem, what we really need to do is we really need very accurate measurements of the strength of these shocks. And that's very hard to do because, as you can see in this image here, the shocks are kind of in the outskirts of the cluster where there are very few photons to work with. So what we essentially need is kind of a new X-ray satellite which has a much better sensitivity in order to kind of do these detailed measurements at these shocks location. And again here, this was already mentioned, the one mission which can do that is the Lynx mission, which is a candidate flagship mission. This mission has a much better sensitivity than Chandra, so can really do this precision measurement of shocks. And at the same time, it has this really good angular resolution, which is really required because you have to kind of measure very precisely this kind of really sharp edge. So for that, you need kind of arc-second resolution. So we really look forward to the future, both in the radio, where we can, basically in the next few years, we should start finding many more of these sources, and in a somewhat more distant future when we have a much more sensitive and better X-ray satellite, hopefully, to our disposal. Thank you.
Thank you, ladies and gentlemen. We're going to talk about how far away that particular galaxy is. We've produced a vast catalog that offers astronomers and research some important, useful answers to the distances of galaxies. In brief, we have a catalog with 166,000 redshift-independent distance estimates. I'll explain more in a second. For 77,000 galaxies now available in NED-D. For those of you not familiar, NED is the NASA IPAC Extragalactic database, and the part of the NED database that deals with these redshift-independent distances we refer to as NED-D. Just to introduce NED a little bit more, NED's mission is to accumulate and place into a central, easily accessible location the data that is published on galaxies beyond our Milky Way, so that astronomers, researchers can access all of the data that they need to and analyze to carry out their research. And what this is showing is an all-sky projection of the approximately 250 million galaxies that are currently cataloged in NED. It's a density projection. But what's interesting in this figure is, of these 250 million galaxies, a rough estimate of the numbers that have redshift-based distances, like Rick was mentioning, based on the recessional velocity of these galaxies and the Hubble law, several million, 5, 6, 7 million or so. The problem with these redshift distances, although more available and abundant and frequently used, honestly, by astronomers, is they're not very accurate, especially for galaxies more nearby. And so it's important to have, in addition to these, distances based on indicators that are independent of a galaxy's recessional velocity. So distances, for example, based on, you've probably heard of these, Cepheid's variable stars were used by Edwin Hubble in 1926 to establish the size scale of our universe, in 1929 to determine its expansion rate. And it's precisely these kinds of distances that allow us to provide astronomers with extremely accurate distances, not only to individual galaxies, but then to combine these distances. And just as in Hubble's time today, ever more data, ever more redshift-independent distances allows us to determine with ever greater precision the true size scale of our universe, its expansion rate or Hubble constant, and by studying these, study variations in the motion of galaxies with respect to the overall expansion. You can see what we call their peculiar motions, peculiar velocities due to their gravitational interactions around clusters, superclusters, like we were just seeing some pretty interesting images of. And the fact is, because of their high value to astronomers, it's thrilling for us actually to be able to announce here at this meeting that we have in fact accumulated, as said in our title, 156,000 estimates for 77,000 galaxies, tabulated from 2,200 individual references. And probably the biggest surprise to us is once you see all of these distance estimates in one place in space, we were stunned to learn that astronomers are currently applying 75 different redshift-independent distance indicators to extragalactic research, all of which we make available, of course. And while the numbers of redshift-independent distance estimates might seem small compared to the overall number of galaxies in NED or the universe, for example, the fact is that we are enjoying, as you can see here, explosive growth in the number of these high-value redshift-independent distances. You can see that as of the end of 2016, we were quite pleased to have reached 107,000 redshift-independent distances for about 28,000 galaxies. But look at the leap to the figures we have now in a single update, reaching 166,000 for 77,000 galaxies. And just to spend a little bit of time on what these individual indicators are, you've of course heard of the Cepheid's variables used by Edwin Hubble. There are type 1a supernovae, but we've plotted here some of these 75 indicators. You're kind of onesies and twosies, but you're looking at the 55 of those indicators that have at least 9 or more measurements, in some cases literally thousands, tens of thousands. And we've plotted the distance scale to kind of put this in perspective on the right in megaparsecs, increasing logarithmically. And you can see, starting on the right, those distance indicators that apply most nearby to literally just beyond the Milky Way. And as we proceed from right to left, you can see the indicators such as type 1a supernovae, gamma ray bursts that apply to distances all the way to the radius of the observable universe, about 14 billion parsecs, 14 gigaparsecs. A quick example of how and why a large distance compilation like ours is useful to astronomers. Say an astronomer wants to know the distance to this particular galaxy, and I show Messier 106 because it's famous in distance scale research because it has the most accurate single measurement of a distance to any galaxy beyond our own local group. The well pinned down to within plus or minus 4% estimate of the distance to this galaxy, 7.6 plus or minus 0.3, 0.4 megaparsecs. Well, suppose you were an astronomer in a hurry, maybe an undergraduate, you went to Wikipedia to look up the distance of this galaxy, and you'd find an estimate shown at the bottom there. I hope you can read that, but 7 plus or minus 0.5 megaparsecs, and that's based on just 2 of the redshift-independent estimates that have been published for this galaxy. But let's compare that to the 100 individual distance estimates that have been published for this galaxy that we have in NED-D. And it's interesting to us that when we analyze, study, take the mean of all the different redshift-independent indicators that you see in this compilation, we come up with an answer of 7.5 plus or minus 0.7 MPC. And I'll stress that while our margin of error appears to be larger than that advertised on Wikipedia, it's actually a more accurate estimate of the true margin of error. And the value obtained is extremely accurate if you compare it with the 7.6 megaparsec distance based on the megamaser distance estimate. So we're so excited about the value of the redshift-independent distances in NED that the entire NED team has written and published a paper that we're very pleased to have accepted by the Astronomical Journal, published literally last week, describing how astronomers and researchers can make use of the redshift-independent distances in NED to improve and enhance their research. And I just want to conclude on the fact that in addition to the redshift-independent distances that we have at NED, this is literally just one part of a large number of other recent advances and coming attractions at NED that basically involve the transformation of NED from what you would formerly have known of as a data lookup service, look up the parameters for an individual galaxy, to literally a data system that allows for true science discoveries to be made. And it's probably the best example of that. Last year, the discovery of 53 superluminous spiral galaxies made by Patrick Ogle, George Halou, members of the NED team, and colleagues, got press and recognition around the world, deservedly. But what's interesting is the discovery of these 53 superluminous spiral galaxies was made by Patrick and colleagues by analyzing nearly 1 million individual galaxies in NED in order to call through and come up with these incredibly important galaxies to galaxy evolution. So just to sum up, it's thrilling at NED to be able to witness and partake in the explosive growth in the distances data as you saw it. And in fact, in all of the extragalactic data. It's exciting as new data continues to come in to keep on top of it so that we can make it available to researchers and astronomers and users of NED to help improve their research. We continue to keep on top of new data as it comes in to continue to make NED as up-to-date and complete as possible for our astronomers and users. And of course, all of the data is attributed to and accredited to and linked to the original astronomers that have provided and published that data. And it is the astronomers and researchers that we're here to serve. It's a pleasure and a privilege, in fact, to do so. So thank you very much, ladies and gentlemen.
All right, thank you, gentlemen. We'll go on to the questions and answers. If you're here in the room and you have a question, please raise your hand. Larry will bring you a microphone, then state your name and affiliation and who your question is for. If you're on the webcast, please queue up your questions using the text chat, and we'll get to Inga to relay those to us. All right, questions here in the room? Ethan.
Hi, this is a question for Reinout.
You are?
I'm Ethan Siegel. I'm from Forbes, and I want to know, we see in the cluster collision you show, we see a lack of radio overlapping with a majority of where the X-ray emission is. And I was wondering if that indicates anything about either the absence of supermassive black holes in that region, or if perhaps it indicates that where we do see the radio emission, that we have active supermassive black holes in those outer regions, and what you can say about that.
That's a very good question, and you're right in your, basically you gave the answer. So we expect actually there are shocks in other locations of the cluster, not only in the region where we see the radio emission, and what we think is actually that at those locations there were no basically active supermassive black holes present. So, because typically there are only a few, say 1 to 3 of these active black holes which launch jets are present in a galaxy cluster. So you have to be a little bit lucky at where they are located in the cluster. So on the other part of the cluster, apparently there were none of such sources present, or at least were active. They were not active at the current times. Of course, they could become active again because the supermassive black holes go through episodes of activity. So at some point, something might start show up there, but not at the current time. So, yeah.
Do you have any idea why they would be located where they are and not where they're not, or is that just they are where they are and they're not where they're not?
Yeah, I think that's more or less the answer, yeah. It's
Thank you.
more random, yeah.
Any other questions here in the room? Okay, we have one down here in the front. Martin?
Thank you, Larry. Martin Ratcliffe, freelance for Niel. Your final slide, I think, showed that most of the signals from your stacked images, which, by the way, is a technique used very often by amateur astronomers who use it all the time. It's fascinating that most of your signals come from what you say is X-ray binaries,
Yeah.
which would indicate a hierarchical growth of primordial supermassive black holes. But you also said there's tentative hints that they're actually massive, supermassive. So can you kind of parse that out a little bit?
Pull that all together,
Yeah.
right. Yes, okay, so to interpret the precise nature of the signals requires quite a bit of detailed work. So what we do is we measure the level of X-ray emission, like I showed from the stacking technique, and we then compare it to the expectation from X-ray binaries, given what we know of the other properties of these galaxies, given the amount of mass these galaxies have, given how fast stars are forming in these galaxies. And that lets us set an upper limit on the amount of active galaxy or black hole growth-related emission from a nuclear black hole. And we find tight constraints on how much of this sort of low-level growth can be occurring. And we then compare that with measurements of the directly detected objects. And we work out what's the number of directly detected objects to the number of objects lying below the individual source detection limit, which we're constraining by the stacking. And the shape of that distribution is what gives us our constraint on the nature of the seeds. Now, I will say that if you ask me to guess how things will play out, and once we have real knowledge about this in 20 years, my guess is we'll probably have a mix of some light seeds and some heavy seeds. And indeed, some of those X-ray binaries that we're detecting, those may be seeds for future supermassive black holes. So, but that's where the constraint is coming from. It's a technical process where you try to determine the nature of the signal. You set constraints on the amount of massive black hole growth that can be occurring, and you compare that to the number of directly detected objects. Yeah.
If I could ask a follow-up question. Have we any convincing evidence at this point of any black holes that you might consider characteristic of massive seeds, that is something between stellar mass black holes and supermassive black holes? Do we have anything in the middle that we're convinced we've really seen it?
There certainly are claims, some of which I think are pretty good, for these so-called intermediate mass black holes, which would be 1,000, 10,000 type solar mass objects. Whether I'd be willing to sort of, bet my house on it, perhaps not. But I think there is certainly very intriguing and good evidence, ever increasing in that direction. So yeah, so I think studies of the local universe and pinning down the distribution of black hole masses in the local universe may be one very powerful way to get further insight into these seeds, because some of these will be relics of the early universe. Yeah.
Do we have any questions online, Inge?
Yes, we do. The first question is from Govert Schilling, for a freelance from the Netherlands, for Reinout. Does studying these radio relics yield any new information about the supermassive black holes?
I think the answer is no. We know that they exist, so they essentially just help us to explain the particle acceleration at shocks, so outside of the supermassive black holes. So they're kind of like, yeah, in that sense, it does not help us to understand much about the black holes themselves. They're more of like a source for us, yeah.
Okay, thank you. The second question is also from Govert, for Ian. Do these results give you any reasons to recalibrate the Hubble parameter?
Well, these results, redshift-independent distances, are the basis for calculating the Hubble parameter. We are simply accumulating and publishing the redshift-independent distances that go into making the estimates of the Hubble constant that you see published. And by providing all of the redshift, essentially all of the redshift-independent distances that have been published, we provide researchers with their own means to analyze the distance estimates in any way they wish and to make their own conclusions about what the expansion rate would be. I just don't want to oversell our part in this. I would consider us more support staff that you could say are positive difference makers that allow the astronomers then to take the data published and make sense out of what the actual expansion rate might be.
I actually had a similar question to what Govert asked, so let me ask it slightly differently. Because you have taken the broad view, looked at all of the reference material independently, and you've compiled multiple independent distance estimates for the same galaxies, and you therefore have some galaxies for which you have different methods from different papers, and maybe there's a chance that some of those were overlooked by some of the other researchers, or maybe you've got some new insight onto how well those multiple different independent, redshift-independent distance indicators are. So the way I would have asked the question Govert asked is, did you come across anything that caused you to say, hey, wait a minute, these multiple methods that are being applied to the same galaxies don't all agree very well? Might that cause you to go back and reassess the redshift distances and the Hubble relation?
On my own part, I'd have to say no. I don't myself get involved in that level of research. I'm simply here to serve the astronomers and researchers that do get involved in that. Although, to answer your question for my own part, we do see anomalous data all the time. Mm-hmm. But it's not our purview at NED to edit or screen or filter the data. Our mission, our mandate, is to make available the data as it is published, unfiltered, unfettered, so that astronomers can then make their own decisions and choices about the data available and which they want to use and exclude. But we do see some interesting...
Well, I see a lot of students in the room. Maybe there's a good thesis project here somewhere.
Well, I just think, as a point of information, Wendy Friedman is giving a plenary talk on that very topic this afternoon.
Right. Good
Nice.
point.
Thanks for mentioning that's important.
We'll see if she mentions Ned. If she doesn't, you can stand up and ask about it.
She knows somebody that's involved.
Inge, are there any other questions back there? Do we have any further questions in here? Anybody? Well, those of you who've been to AAS press briefings before know that I always keep a few questions in reserve. I have one for Niel. Could you explain or just describe how this particular field is chosen or was chosen, which came first, the Hubble observations or the Chandra observations, and how generally do these various deep fields at different wavelengths get coordinated?
Right. So this field, the Chandra Deep Field South, was originally started by a team headed by Riccardo Giacconi, who many of you probably know as a very distinguished X-ray astronomer, winner of the Nobel Prize in physics. And they chose this field to have low contamination by our own galaxy, to have a very clean line of sight out into the distant universe. And they started this field pretty fresh. I believe the Chandra observations were the initial motivating factor. Now, subsequently, this field has become one of the most intensively studied fields in the entire sky. There are a couple of others that are competitive, but this one is arguably the best now. And for example, many of you surely know of the famous Hubble Ultra Deep Field, one of the most famous images in all of astronomy. That's located right in the center of the Chandra Deep Field South. And there's been many other extensive projects with the Hubble Space Telescope. You may have heard of the GOODS project or the GEMS project, or more recently CANDLES. All of those cover substantial fractions of the Chandra Deep Field South. And then again, we are now blessed to have fantastic spectroscopic databases gathered by the largest ground-based telescopes on Earth. Fantastic coverage in the infrared, both imaging as well as spectroscopy, both from the ground and from space, with Spitzer and with Herschel in particular. And then now in the submillimeter, ALMA is opening up this sky region and letting us study the growth of black holes in the first forming massive galaxies out at redshifts of 2 to 3 to 4. And then in the radio as well, the VLA and the expanded VLA are getting better and better data as well. So yeah, this field started off with sort of an X-ray driver, but it is now snowballed. And that's what's kept it fresh. People often ask me, how can you work on this field for 17 years? Don't you get bored? And the answer is no, I don't. Because first of all, the X-ray data are getting better and better over the years. And secondly, the multi-wavelength data are getting better and better over the years and injecting new ways of looking at the sources we already know, new ways of understanding them more deeply. So I think all that, together is what keeps this exciting for me. Yeah.
And this field is roughly how big compared, say, to the size of the full moon?
Yeah, it's about 60% the size of the full moon on the sky. Okay. And in that's where we get the somewhat over 1,000 X-ray sources. Okay. Yeah.
All right, any other questions? Good, got one over here from John.
I guess this one's also for Niel.
And you are?
I'm John Wenz with Astronomy Magazine.
Thank you.
And I guess this just has to do with some of the ages of the galaxies you're seeing in this field. Mm-hmm. Are you getting close to some of the early, just post-reionization galaxies, or is that still something you'll need more sensitive instruments for?
Yeah, so certainly we have in this field, this field is so intense that many of those galaxies you have heard about, galaxies found out to redshifts of about 10 now, have been found in this field. And but there's only small numbers of them. So the particular results I showed you today were ones where, based on that stacking technique, we could obtain extremely long exposures. But I will tell you, we actually have collected all of the galaxies out to redshifts of about 10, and we've stacked all them up too. So far, we're just getting non-detections out there because the sample size is small, and so we can't get these enormous billions of seconds of effective Chandra exposure yet. But in the future, when JWST comes, trust me, for the first day, I'll be there pounding at it. We have the codes up and ready to go. And so just insert JWST data, out come, hopefully exciting discoveries. Yeah.
Great, thank you.
Yeah.
All right, well, it sounds like we're coming to a close. I'd like to thank our speakers again, and also thank all of you for coming. Thanks to those who tuned in on the webcast. The next briefing will be this afternoon at 2:15. It'll be latest results from the Sloan Digital Sky Survey, so we'll be looking at another big data project that's scanning the universe out to the most distant regions. I wanted to mention that the briefings from yesterday, the webcasts of those briefings have been archived now on our archived webcast page, so if you missed the briefing or want to check anything there, you can find that on our website. And with that, I'll say thanks a lot and see you this afternoon. realize they were going to actually print this.
Oh, yeah.